You drop a cup, it shatters on the floor, and then you wait. You wait for the pieces to jump back together, fly up into your hand, and become a cup again. You're going to be waiting a long time. This is so obvious that it sounds stupid to even say it. Of course, broken cups don't reassemble themselves. Of course, spilled milk doesn't flow back into the glass. But here's the thing that should bother you. Why not? No, seriously, why not? Because if you look at the laws of physics, all of them, the laws of gravity, electricity, magnetism, nuclear forces, every single one of them works perfectly well in reverse. Run the movie backwards and the physics still makes sense. A planet orbiting the sun, film it, reverse it, and it's still a valid orbit. The physics doesn't care which direction time goes. Every collision of atoms, every interaction of particles, it all works forwards and backwards equally well. So if all the fundamental laws are reversible, why is the world so obviously not? We remember the past. We don't remember the future. Think about that. We have memories of yesterday, last year, our childhood, but the future, nothing. Blank. We can guess, we can predict, we can hope, but we don't remember it. We feel like we can affect the future. We make choices, we take actions, we try to change what's going to happen. But the past? It's done. Fixed. You can regret it, you can feel remorse about it, but you can't change it. This difference between past and future is so built into our experience that we barely notice it. But it's strange. It's really strange, because the atoms don't know the difference. And now you might think there must be some law somewhere in physics that says time only goes forward, some rule that says particles can only move this way, not that way, some fundamental principle that makes the past different from the future. But we haven't found it. After centuries of looking, we haven't found any law that distinguishes past from future. The equations work both ways. So where does the... Let me show you something. Take a box, divide it in half with a partition. Put white gas molecules on one side, black gas molecules on the other. Now remove the partition. What happens? The gases mix. Obviously, the white molecules drift into the black side, the black molecules drift into the white side. And pretty soon, you have a uniform gray mixture everywhere. Now, if you wait long enough, will the gases ever unmix? Will all the white molecules ever spontaneously go back to one side and all the black molecules go back to the other? Technically, yes, it's possible. The laws of physics allow it. If every single molecule happened to be moving in exactly the right direction, at exactly the right speed, they could all end up separated again. But the chances of this happening are so small, so incredibly tiny, that you would have to wait longer than the age of the universe. Much, much longer. The number of years you'd have to wait has more digits than there are atoms in the observable universe. So it's not going to happen. Or push a heavy block across the floor. It slides, slows down, and stops. The friction between the block and the floor brings it to rest. Now wait. Wait for the block to suddenly start moving again. Wait for the floor to push it back toward your hand. You're going to be waiting forever. The energy of the moving block didn't disappear. Energy never disappears. It transformed. It became heat. The friction warmed up the floor just a tiny bit. The organized motion of the block, all those atoms moving together in the same direction, became disorganized motion. Atoms in the floor jiggling randomly in all directions. That's entropy, right there in a sliding block. The organized motion became disorganized heat. The energy spread out. The information about which direction things were moving got lost in the chaos of random thermal jiggling. Every time you see friction, every time something slows down and stops, you're watching entropy increase. You're watching organized motion become disorganized heat. You're watching the arrow of time in action. Your car brakes. Entropy increases. A ball bouncing lower and lower until it stops. Entropy increases. A pendulum slowly coming to rest. Entropy increases. It's everywhere. It's constant. It's relentless.
But, why doesn't the block ever slide back? Why don't the gases unmix? Each individual molecule is just bouncing around randomly. There's nothing stopping any particular molecule from going left or right, so why don't they ever all go to one side? It's about counting. It's about the number of ways things can be arranged. Think of it this way. You shuffle a deck of cards. What are the chances that after shuffling, all the hearts are together, all the diamonds are together, all the clubs are together, and all the spades are together? Almost zero. Not because any particular arrangement is forbidden. Any specific arrangement of 52 cards is equally unlikely. But there's only one way to have them perfectly sorted, and there are billions and billions of ways to have them mixed up. So when you shuffle, you almost certainly go from order to disorder, not because of any fundamental law, but because there are so many more ways to be disordered than to be ordered. And that's entropy. Entropy is, well, you can think of it as a measure of disorder, but more precisely, it's a measure of how many different microscopic arrangements could produce the same macroscopic appearance. When the gas is separated, white on one side, black on the other, there's only a limited number of ways the molecules can be arranged while still looking separated. But when it's all mixed together, there are astronomically more arrangements that all look the same, gray everywhere. So the gas mixes not because mixing is a law of physics, but because there are vastly more mixed states than unmixed states. It's just probability, overwhelming, crushing, inevitable probability. Now, watch this. The laws of physics don't have a direction, but probability does. Probability says you almost always go from less likely states to more likely states, from fewer arrangements to more arrangements, from order to disorder. And that's where the arrow of time comes from. The past is when there was more order. The future is when there will be less order. We remember the past because our brains record information, and recording information requires order. We can't remember the future because it hasn't been ordered yet. Let me put it another way. Every time you break an egg, you're increasing the entropy of the universe. The egg had order, shell intact, yolk in place, everything arranged just so. The broken egg has less order, pieces scattered, yolk spreading, chaos. Could the egg unbreak? Could all those pieces fly back together and reform a perfect egg? In principle, yes. Every atom could reverse its motion, but the chances are so impossibly small that it will never happen in the lifetime of the universe. So the egg stays broken and time moves forward. This is profound. Really think about this. The difference between past and future, this thing that feels so fundamental to our existence, it doesn't come from the laws of physics at all. It comes from statistics. It comes from counting. It comes from the simple fact that there are more ways to be messy than to be neat. Every moment of your life, you're riding the wave of increasing entropy. Every breath you take, every thought you think, every action you perform, it all increases the disorder of the universe just a little bit. And that's why time has a direction. But wait, there's a problem. If entropy always increases, if everything always moves toward disorder, then why is there any order at all? Why isn't the universe just a uniform gray soup of randomly scattered particles? Look around you. There are stars, galaxies, planets. There's life. There's you sitting there with your incredibly organized brain full of neurons firing in precise patterns. How did all this order come to exist in a universe that's supposed to be falling apart? The answer takes us back to the very beginning, the Big Bang. For some reason, and honestly we don't fully understand why, the universe started in a state of incredibly low entropy, extremely high order. Everything was packed together, organized in a very specific way. And ever since then, entropy has been increasing. The universe has been unwinding, moving from that initial order toward eventual disorder. So when you see a star burning in the sky, you're not seeing order being created from nothing. You're seeing the slow release of the order that was built into the universe from the beginning. The star is spending the cosmic inheritance, you might say. Think about it this way. Imagine you have a giant spring wound up incredibly tight. That's the early universe, full of potential, full of stored order. And everything that has happened since, every galaxy forming, every star igniting, every planet cooling, every life form evolving, it's all just the spring unwinding. We're living off the low entropy of the past.
Now, you might ask, if the laws of physics are reversible, couldn't we argue that the future also has low entropy? Couldn't we say that the universe will eventually wind back up again? No, and here's why. Suppose you're looking at a box of gas that's half mixed. Some white molecules, some black molecules, kind of swirled together, but not completely uniform. Now I ask you, what was this gas doing a few minutes ago? And what will it be doing a few minutes from now? If you assume the mixing happened by accident, by random fluctuation, then the most likely answer is that it was more mixed before, and it will be more mixed after. The current partial separation is just a temporary fluctuation, and the gas is on its way back to being fully mixed. But that's not what we observe. We observe that the past had more order and the future has less. The gas was separated before, and it will be fully mixed after. This tells us something crucial. The order we see in the world is not due to random fluctuations. It's not an accident. It's a memory of an initial state of very high order. Suppose you look at one corner of a room and you see some order. Maybe the gas molecules there happen to be arranged in an unusual pattern. If this order came from a random fluctuation, then you would expect the rest of the room to be completely disordered. The fluctuation would be local. But when astronomers point their telescopes at new parts of the sky, parts they've never looked at before, they find order there too. Stars burning, galaxies spinning, the same patterns everywhere. This tells us the order is not a fluctuation. The order is universal. It came from the beginning. So the entire arrow of time, the entire distinction between past and future traces back to one fact. The universe started with low entropy. Everything else follows from that. Why do we remember the past but not the future? Because memories are records, and records require order. The low entropy of the past allows records to be formed. The high entropy of the future doesn't. The whole structure of our experience, cause and effect, memory and anticipation, birth and death, it all traces back to entropy. The Big Bang wasn't just an explosion. It was an explosion of order, a release of potential. And everything that has happened since, every star, every planet, every life form, every thought you've ever had is riding that wave of increasing entropy. We don't know why the universe started that way. We don't know what set up those initial conditions. It remains one of the great mysteries. But we do know this. The arrow of time points from low entropy to high entropy, from order to disorder, from the past to the future. And there's no escaping it. Now, people sometimes get confused. They look around and they see order. They see crystals forming. They see plants growing. They see babies being born and developing into complex adults. And they ask, doesn't life violate entropy? Aren't living things becoming more ordered over time, not less? No, life doesn't violate entropy, not even close. Yes, a growing plant becomes more ordered. Yes, a developing embryo becomes more complex. Yes, your brain is an incredibly organized structure, but none of this happens for free. To grow, a plant absorbs sunlight. That sunlight is low entropy, energy, organized, concentrated, coming from one direction. The plant uses that energy to build its structures, and in the process, it radiates heat back into the environment. That heat is high entropy energy, disorganized, spread out, going in all directions. The total entropy, plant plus environment, increases, always. You are the same way. You eat food. Food is organized, complex molecules arranged in specific patterns. Your body breaks down that food, extracts the useful energy, builds and repairs your tissues, and in the process, you radiate heat. You exhale carbon dioxide. You produce waste. The order in your body is borrowed. It comes from the order in your food, which came from the order in the sunlight, which came from the order in the gas cloud that formed the sun, which came from the Big Bang. So you are not fighting entropy, you are surfing it. Life is not a violation of the second law of thermodynamics. Life is a particularly interesting way of increasing entropy. We are entropy-increasing machines that happen to be conscious. Think about that for a moment. Every breath you take increases the entropy of the universe. Every thought you think, because thinking requires energy, and energy use produces heat, increases the entropy of the universe. Every moment you're alive, you're contributing to the great unwinding. But along the way, along this process of increasing entropy, you get to experience things. You get to think. You get to wonder. You get to love and create and discover. Life is what entropy looks like when it gets complicated.
And the order that makes you possible, the low entropy that allows your existence, it's not just from yesterday's breakfast. It traces back through an unbroken chain, back through the food chain, back through the ecosystem, back through the formation of the earth, back through the ignition of the sun, back through the collapse of gas clouds, back through the formation of the first stars, back all the way back to whatever happened at the beginning. You are connected to the origin of the universe, not metaphorically, physically. The arrow of time that runs through you is the same arrow that runs through everything. The entropy that governs your life is the same entropy that governs the stars. When we study physics, we study the fundamental laws, the equations that govern particles and forces and fields. And these laws are beautiful, they're elegant, they're reversible, but they don't tell the whole story. The laws tell you what can happen. They don't tell you what does happen. For that, you need initial conditions. You need to know where things started. And the arrow of time, the distinction between past and future, comes from those initial conditions, not from the laws themselves. This is a profound distinction. The laws are eternal and symmetric. The world is temporal and asymmetric. The difference comes from history, not from physics. We often think of physics as telling us what the world is, but really, physics tells us what the world can be. The world itself, with all its complexity and history and direction, is one particular realization of those possibilities, one particular path through the space of what's allowed. Why this path? Why these initial conditions? Why this arrow of time? We don't know. Maybe we'll figure it out someday. Maybe we won't. But the question itself, the question of why the universe is the way it is, rather than some other way, that question is part of what makes physics so fascinating. We're not just cataloging facts, we're trying to understand why reality is real, why things happen, why time flows, why we're here at all. Now, some people find this depressing. The universe is winding down. Everything falls apart eventually. Every structure, no matter how beautiful or complex, will ultimately dissolve into chaos. But I don't see it that way. Think about what it means to be alive right now. You exist in this narrow window, this brief era between the ordered past and the disordered future, when complexity is possible, when stars can burn, when planets can form, when molecules can arrange themselves into living things. You are not separate from this process. You are this process. You are entropy increasing in a particularly interesting way. So when I say we're all going to the same place, I mean it literally. Every structure dissolves. Every order becomes disorder. Every complex thing eventually falls apart. Stars burn out, planets cool, life ends, civilizations crumble. Eventually, given enough time, the universe reaches maximum entropy, heat death, equilibrium, nothing more happening ever again. But don't let that make you sad.
The fact that entropy increases, the fact that time moves forward, the fact that everything eventually ends, this is not a flaw in the universe. This is what makes the universe interesting. Without increasing entropy, nothing would happen. There would be no change, no flow, no story, just static equilibrium forever. The arrow of time is what gives us moments. The march toward disorder is what gives us events. The slow unwinding of the cosmic spring is what gives us everything. You exist because entropy increases. You experience time because entropy increases. You can make choices and have effects because entropy increases. So yes, we're all going to the same place, but the journey is everything. And right now, you're on it. You are made of atoms that were forged in ancient stars. You are organized by patterns that trace back to the beginning of time. You are conscious in a universe that is mostly not. And for this brief flicker, this tiny window between the ordered past and the disordered future, you get to be here. The universe is winding down. But right now, in this moment, it's still wound up enough for you to exist, for you to think, for you to ask questions about why anything is the way it is. That's not tragedy. That's something, isn't it? The arrow only points one way,